Alright guys, sorry I can't be in class to give these notes, but my mom has to have some surgery and I've got to be out today, so here are your notes over work and energy. This is the last unit we're going to do before the end of the 9 weeks, so you're going to have a test basically next Tuesday over this. So remember your car project is due on Monday next week, so you got a week left. Remember the board and ramp is either going to be in my room or next door with Miss Harper. So here are the notes on work and energy. Alright, to start with, work is the product of the magnitudes of the component of a force along the direction of a displacement and the displacement. Basically, this is a fancy way of saying when you apply a force to something, it will move a distance. If you apply force to something, it will move a distance. So it's going to be the product multiplying force times distance together. So a force that causes the displacement of an object does work on that object. The SI unit for work is the joule. We're going to start working with joules a lot. You probably started working with joules back in chemistry last year. If work is being done at an angle, like on page 169 in your book, we can always add cosine at the end of this. So work is equals force times distance times the cosine of our angle. If our angle is 0, if it doesn't give an angle, the cosine of 0 is 1, so it works out for us. Here I want to talk about, because we're going back into forces. We talked about forces back in chapter 4. Can you find a force with just a mass? Say if I gave you a problem and let's say that I gave you a mass and not a force. Can you find a force with that mass? Yes, you can, because the force of gravity working on that mass, when gravity pulls on your mass, it's your weight, which is a force. And what's the unit for force? It's a Newton. So if I give you a mass, you can still find the force if you go mass times gravity. Don't forget that. Alright. The sign for work is important also. You can have positive work and negative work. 99% of the time we're going to be working with positive work. Positive work means that the work being done is in the same direction as the object's displacement. I apply a force to something, that force moves the object in the direction that the force is going. You're mostly, in this class, this is pretty much all you're going to see. Negative work is in the opposite direction of the object's displacement. If you look on page 170 of your textbook, they will show you examples of this. Alright, the first type of energy we're going to talk about is kinetic energy. Kinetic energy is the energy of an object because of its motion. Anything that is moving has kinetic energy, because kinetic energy is 1/2 times the mass times the velocity squared. Only the velocity is squared in this, not the mass velocity. Just velocity is squared. So kinetic energy depends on the mass of the object and the speed of the object. The unit for energy, any energy, whether it's kinetic, potential, mechanical, whatever energy we're talking about, is always in joules, just like work was in joules. And that's where we get the work kinetic energy theorem. We said work happens when you apply a force to something and that force causes it to move a distance, and work was in joules. Well, if it's moving a distance, just in that, it's moving. And if it's moving, it also has kinetic energy. So we say that work is equal to kinetic energy. And when we start working the problems, you're going to see that I have a very long formula for this. And you'll be able to pick and choose the parts that you want to use. We started doing that in another chapter, but we're going to start doing a lot more here. The next type of energy we're going to talk about is potential energy. Potential energy, this is the energy associated with an object due to the position of the object, due to where its position is. And potential energy has many, many types of subsets. And the first one we're going to talk about is gravitational potential energy. It basically starts out the same way as potential energy, the potential energy associated with an object due to the position of the object, but then this is where you get more specific, relative to the Earth or some other gravitational source. So basically, we're on Earth. It's the basic gravitational potential energy of things here on Earth. Gravitational potential energy depends on the height from a 0 point. Like if I drop my pen in class, I'm going to call the 0 point probably the floor. But if I drop the pen off the side of a building, I can call my 0 point the ground. So you have to have a 0 point to start from, or something's just going to fall forever. So the formula for gravitational potential energy is mass times gravity times height. Mass times gravity times height. We'll give you this, and again, what's the unit for potential energy? Just like all energies, it's in joules. Alright, another type of potential energy is elastic potential energy. This is the potential energy in a stretched or compressed elastic object. A rubber band, a slinky, bungee cord, anything that will stretch will have elastic potential energy associated with it. The elastic potential energy is 1/2 K times x squared, where K is your spring constant. The spring constant is in, we'll talk more about that in the problems, but it's a Newton per meter, and the distance it's stretched or compressed, that's your x. So x isn't just a single distance. If I give you a resting rubber band and a stretched rubber band, it would be the difference between those two lengths. So let's say that sitting on the table it is, let's say 0.5 centimeters long, and stretched it's 1.5 centimeters long. So what's x? Well, x is going to be the difference between the two. X would be 1 meter long, or centimeter. I don't remember what my unit was there. So the spring constant is a parameter that expresses how resistant a spring is to being compressed or stretched. That's what your K will be. And you'll work some problems like this. Alright, now we're going to start talking about mechanical energies. This is the sum of kinetic energy and all forms of potential energy together. So mechanical energy is your kinetic energy plus all the different forms of potential energy added together. So mechanical energy is often what we call conserved. That means whatever energy you start with will equal the energy you end with. And basically MEI, the initial mechanical energy, will equal your final mechanical energy. And a lot of times we write it like this. You'll see me actually write it like this more times than not. I'll go PEI plus KEI equals PEF plus KEF. And then you'll plug in, because remember we talked about kinetic energy here, potential energy, kinetic energy. I don't know, my subscripts didn't work here. But basically it's just the formulas for these pushed in. Remember, energy is always going to be in joules. Have you remember seeing a pendulum that swings back and forth? I'll show you in class also. But a pendulum could swing around and around and around. Alright, let's say that I pull a pendulum all the way up to this point. Does it have potential energy or kinetic energy at this point? Well, if I'm holding it, is it moving? No, so if it's not moving, there is no kinetic energy there. So what kind of energy is it? It's all going to be potential energy at this point. So then I let go and it swings down to this position. And it's going to be halfway between here and this bottom point. Well, at this point, is it moving? Yes. So at this point, it will have kinetic energy. But it still has further it can go down, so it will also have potential energy. It gets down to this part. Can it go? Is it at its lowest point? Yes. So this would be considered its 0 point. So there's no potential energy here. It would all be kinetic energy. And it swings up to this halfway between up and down. You would then have potential energy and kinetic energy. All the way back up here again, it's potential energy. And it'll swing back and forth, transferring between all of these. So if I had 100 joules right here, I would have 50 joules and 50 joules here. Back to 100 joules here. 50 joules and 50 joules. And then back to 100 joules of energy. As it swings back and forth, it's just transferring between the different states of potential and kinetic energy. This might be the biggest key concept of the entire semester. That's why I've got it bolded here. Energy is never created or destroyed. It only transfers between states. It will only do this. You cannot create energy. Energy is already all around us. It's just harnessing it and using it. So energy is never created or destroyed. It only transfers between states. You cannot create new energy. Mechanical energy is not conserved in the presence of friction. So when things rub against each other, we've talked about friction before. This does not mean that the total energy is not the same, only that the energy is turned into other forms of energy that are harder to account for. A lot of people don't understand this, that heat is a form of energy. Like, whenever heat is given off of something, it's losing energy. And that's just another form that we use to gauge energy by. So in a car crash, when things hit together, you're going to have a transfer of energy from car to car, but you're also going to have friction there. And that friction causes heat, which dissipates the energy out. And that's just something else we would have to take into account. So energy is never created or destroyed, only transfers between states. Okay, last slide is about power. Power is the rate at which energy is transformed. So power is going to be work divided by time. Work divided by time. Also, you can find it with power equals force times velocity. But most of the time we use work divided by time. The SI unit for power is the watt. So how many watts you have, kind of like your light bulbs, have a power rating in watts. Machines with different power ratings do the same work at different time intervals. So let's say that I have a lawnmower that is 5 horsepower, and I have a lawnmower that's 10 horsepower. Can they both cut the same lawn? Yes, they both can do the same amount of work. But the 10 horsepower mower will cut the lawn twice as fast as the 5 horsepower motor. That's how power works. Alright, let's go back and talk about work and power together for a second. Let's say that I'm at the stairs, and I walk up the stairs, and then I run up the stairs. Which one did more work? Which one of these did I use to do more work? If you answered running, you were wrong. If you answered walking, you were wrong. Because walking and running, neither one of those work. The formula for work says nothing about how much time it takes for you to do it. It's actually the same. Your work, whether you walk or run up the stairs, will be exactly the same, because work is force times distance. But what if I walk up the stairs and run up the stairs, and I'm looking for how much power, which one uses more power? That's where you're going to get into this, because when you run up the stairs, it's taking less time, so you're going to use, you'll have more power. Hope that explains the difference between work and power, because sometimes people get this confused. If you're traveling the same distance, no matter how fast you're going, you're going to use the same amount of work. But that will change the amount of power you use. So this is the end of the notes. Watch them again if you need to, or ask me questions when I get back. Well, now you're going to start working on the workbook problems, and I've got videos for those too.